Good morning, all my honors chemistry students. Welcome to our very first podcast for our chemistry lecture here on Chapter 11 on Modern Atomic Theory. Yes, I'm sitting in a room by myself talking out loud. All right, good picture of that, huh? All right, here's evolution, the atomic models. We've already talked about this. You've done your timelines on this, so we're going to go very quickly through this. You guys can recognize that John Dalton was the very first one to even start to say that there was an atom and that it did have some tiny spheres, but this is all he thought it was a teeny little atom, nothing about protons, neutrons, and electrons. Now what this chapter is we are really going to take a look at J. Thomson and how he discovered electrons. Remember that they are negative in nature, and he talked about that if you have the sphere, which he talked about it being a positively charged material, that you would have these electrons stuck. No rhyme or reason, they'd just be stuck somewhere in this positively charged material, no rhyme or reason. If you recall, I showed you this demonstration in class with the cathode ray tube where I had the magnet and all that electricity and I was worried about getting shocked. This was the discovery of electrons. And then we talked about Rutherford and that gold foil experiment where he shot that radiation beam through a lead block and some of the beams bounced back, and that's when he was able to discover our dense nucleus. Now, what we are going to be taking a look at is what are these electrons really doing, and that's what you did in class today. You were looking at all those different colors, and that was those electrons emitting light. And so Newton came along and thought that light was made of particles. Now, this probably doesn't seem like a big thing to you or I because we see light, we use light, that's the world that we live in. By 1900, most people believed that light was made of waves. So Newton originally thought that light came to us in these very, very small, tiny packets of energy called a photon, and that they were so incredibly small and so close together that that's why people believe that they are wave-like, but he also believed that they were made of particles. This is still a theory, it's not proved today, but most people believe that light is coming to us as a wave. It doesn't really matter, it's not going to make a difference between your life or mine, but that all these electromagnetic waves come to us by forms of different types of radiation. So just like anything else, we have high amounts of energy, and then we also have very low amounts of energy. Well, I think you guys can probably look at this next slide and realize if I take a look at this, what is high energy and what is low energy? So we have these gamma rays. This is the nuclear end of the scale. That's how strong those waves are. X-rays, I think you guys know those are pretty strong. To be able to see our nice skeletal being that we have. 1 second here, I need to pause this. Okay, sorry about that. I had to pause this for just a second. So we're talking about all these different types of energy, and I think you guys know that X-rays are pretty high energy, but radio waves, you guys can picture with your own radio in your vehicle that sometimes a radio station comes in really well and sometimes it doesn't. It's because those radio waves don't have a lot of energy and they're easily diffused or deflected by our environment. So if we go back to our other slide over here, we can see that we have some very, very high energy electromagnetic radiation, which would be things like gamma rays and X-rays. And then we have things that are very low energy, like our radio waves. And they all come in at different frequencies and different wavelengths. And so that's what we're talking about in class today, that our visible spectrum is right in here, right in the middle in terms of our energy amount, and they all come in with different frequencies and wavelengths. And so let's take a look at that. So if we take a look a couple slides here, we can see properties of waves. All electromagnetic waves travel at 3.00 times 10 to the 8th meters per second, and that is in a vacuum because obviously these particles and waves can be deflected by things, but we can measure these as the speed of light, that the wavelengths between crusts to crusts or troughs to troughs, and you can see that they have shorter and longer wavelengths. Well, if I take a look at this, the wavelengths are these distances. So you can see if you think of a slinky, how you can stretch out the slinky or make it really small. The same thing about the frequency, the number of waves pass a point per second. Well, if I take a look at what that is going to be measured in what's called a hertz. Not the Hertz car company. Whoops. And that is abbreviated Hz. And what that is the number of waves to pass a point per second. So a hertz is a 1 over a second. So if I take a look at this and apply this to the colors that you guys saw in class today, you can see that if I'm on the Roy G. Biv spectrum, the longer wavelengths are going to be red in color. And if they are in red in color, they have the longest wavelength, that also means that they are at the lowest frequency, a little bit harder to see. Then if we take a look at violet, they have the shortest wavelength, so I'm at the other end of the spectrum, then they are going to have the highest frequency. And I think I forgot to mention that this shape right here is a Greek letter lambda nu, and that is abbreviation for frequency. So this is frequency right here, and then wavelength is the Greek letter lambda. Okay, so as we take a look, we must have a table formula. I know I did say we were going to be dusting off our calculators, but we're not going to be doing a ton of calculation in this unit. So speed of light, don't ask me why, it's abbreviated by the letter C, is equal to our wavelength, lambda, times our Greek letter nu, which is our frequency. And so we were able to take a look at our speed of light and be able to establish all different kinds of colors, like what you guys did in class today. So if we look at that, you guys can see in terms of wavelength, all the different colors of wavelengths, and our visible spectrum right here, right in the middle, Roy G. Biv, like I was just talking about, longest to shortest wavelengths. And again, all these radio waves, you can see they're very long. And over down here, gamma rays, very, very high energy. And so all of these are make up the electromagnetic spectrum. All right, so how did we see that light today? Why did we see that light today? So elements emit light when they are excited and passing electric discharge through its gas or vapor form. So what you were doing, you were getting the cells a little bit wet, you were heating them up, and you were getting into the gaseous phase. So here's my little old electron. It's sitting in its ground state. You can kind of think of this that probably at 2 or 3 in the morning, you are sitting in your house. Who knows where you are? Maybe you're still watching a movie, maybe you're comfortably in bed, but you're somewhere in your ground state. You're at home. Then some energy is brought into your system, and what's going to happen to you? You're going to become very excited, as you can see this electron has become. Well, what happens is this electron has the ability to absorb energy just like our body can with caffeine or whatever it is, but we have to get rid of it. So does the electron. And when the electron jumps up to another energy level, as you can see here, it's left that home and it's jumped up to another energy level. When it falls back down, that's when light is going to be emitted. So what you saw today were electrons getting super excited, jumping up, falling down, you saw light. Jumping up, falling down, you saw pink light. You saw orange, you saw red, whatever it was. These electrons were getting excited. They are accepting this energy from a photon from our Bunsen burners, and they are jumping up to higher energy level and falling back down, and that's when you were able to observe something. Pretty cool, don't you think? All right, so here's our flame test. The same thing, is just another picture of it, in that this energy is coming in, the electrons jump out, and when they fall back down to these whatever energy level it is, they are going to emit light. And depending upon what colors you guys saw, depends upon what wavelength they're going to happen at. So you can see up at the top of the screen here, we have violet, nm is nanometers, by the way, it's just the distance of wavelength, and all the way to red. Well, if we take a look, you can see that they are all falling down to this certain level when they are emitting their light. And we're going to understand what all these energy levels are a little bit later, and how many electrons can fit in each one of these and what shape they are. So it becomes a pretty complicated model here before too long. Now this is our bright line spectra, which is what you guys are going to look at tomorrow in class. Electrons jump to a higher energy level when excited, like we talked about, causing, they're absorbing that photon or the electric voltage, and it's released and electrons fall down to lower energy levels, and this is when I see the colors. So we talked about our fingerprints today. Well, this would be a specific fingerprint of one of the elements. And this is what we're going to take a look at tomorrow. We're going to look at these bright line spectra so you can see the differences. What you saw a lot of things that were orange today and a lot of things that red. Is there a difference between them? Absolutely. And again, this is just another thing that's showing you that the bright line spectrum, we're going to take this gas discharge tube, we're going to have hydrogen, we're going to have mercury, run it through a prism, which is going to be our spectroscope, and we're going to see all these different bright lines. These, you guys, are the fingerprints of every single element. Not every element will have these colors. Some will have many bands of the same color, and they all will be measurable. All right, I am done for today, you guys, and have an awesome day, and I will see you in class very soon.